Hello, you're welcome to my channel. Now in this video, I'm going to show you how to make use of the DI method. Now the DI method is just a simplified form or a simplified version of the integration by parts formula. So if you have a certain function to integrate and you want to make use of integration by part, because that is the only way, okay, you can apply the DI method over here. It is very short. In the cases where you have to apply the DI method twice, like this one, or 3 times, like this one, or infinitely many times, like this one. But it's not like that, though. Okay, so I am going to start with the first one, which is very simple, right? And I'm going to just put this down for you, DI. So the DI method is in a way that this D here stands for differentiate, right? And this I here is for integrate. Okay, so we put down the D and the I, which means we want to differentiate a certain thing and we want to integrate a certain thing. Okay, great. And another thing you should also pick up is when you put down the DI, before the choice of the functions, always remember to put addition, subtraction, and continue like that. But it will not be necessary that we continue further. Anyway, you will see that. So we look at these functions. Let me put this. It's a kind of a table. Right? Now these functions, which of them should we differentiate and which of them should we integrate? Now the wise choice is to differentiate this polynomial term, x, alright? Because when you differentiate it, the power will reduce and it becomes a constant. And you can deal with the integral of the other function. You don't differentiate this one and integrate this one. No, you will not have an end. So the wise choice is to differentiate x. So we put it down under the differentiate. You don't differentiate it first. You write it down. And you now put down the other one, that is e to the power x. You now differentiate it. Remember to put plus, minus, like that. So when you differentiate x, with respect to x, because we are integrating over the x variable, we are going to have just 1. And when you integrate e to the power of x, in fact, that function remains unchanged when you differentiate and when you integrate. Alright. Okay. Now we've reached a constant. If we differentiate this again, because we can actually apply this more than once, in cases like this, where we need to apply the integration by parts more than once. So if you differentiate this again, you are going to have 0. So at that point, you don't go further. You stop, okay? And maybe we can erase this. But these two are very important. Now this is how we do it. When you are done differentiating and integrating, what you need to do is to go ahead and multiply the diagonals. Okay? Multiply this with this. Then, also multiply this one out. Alright? So we are going to have that this is going to be equal to the product of the diagonals, x times e to the power of x. So we just put it down. X times e to the power of x. Now, we multiply the product of the last row, alright? Like I've circled it here. And when we do that, we integrate that one. So if you multiply e to the power x with 1, with negative 1, remember, that will be negative e to the power x. And you integrate that, that will be minus the integral of e to the power of x, and you put down the dx. So from this table, we multiply the diagonals, we put it down, and we integrate the product of the last row, which is just the integral of negative e to the power x. You know, when you multiply with 1, that is what you get. Great. So from here, we can just integrate e to the power of x, and as we know it, it is just e to the power of x, and we put down this one. And when we simplify this, we are going to have that x minus 1, then e to the power of x. That is the result, alright? We just add an arbitrary constant, and that ends it for the first question. Okay, so maybe I will just equate it to the result and move on to another question. Now, for the second question, we have a special case here. This is x squared, and this is e to the power of negative x. Well, the same way, we still put down the d and still put down the I over here, okay, as a table. And then, remember, you alternate these signs, plus, minus, just keep alternating like that. Great. So the next thing we'd like to do is to differentiate this x squared and integrate this other one, e to the power of x. So, by differentiating x squared, we put down the x squared and we put down the e to the power minus x. We differentiate x squared, we're going to have 2x. We integrate e to the power of negative x, we're going to have negative e to the power of negative x. You know, when you have e to the power of, let's say, a constant, in this case the constant is negative 1, if you integrate this, you're going to have e to the power of ax divided by that. So since this constant is negative 1, you divide by negative 1, that will just be negative in front. Then 1 as a denominator, it does not mean anything for us when we are considering divisions. Now, here, after differentiating it once and integrating it once, this polynomial term, okay, is not yet a constant term. It's still 2x. So we still have to make it, we still have to go further, alright? So in going further, we differentiate this again for the second time. We are going to have 2. Remember, this is plus for this one. This is minus for this one. So we go again with 2. Okay, now we've reached a constant position, so we don't need to differentiate further, right? So I've cleaned the negative. Now we integrate this again. In fact, we're going to have e to the power of negative x. Just check that out. Great. Because the negative from this, we'll cancel out with that. And then we can now go ahead and do as usual. We go ahead and multiply the diagonals, and integrate the product of the last row. Remember the sign in front. Okay? So like we did here, we multiply the diagonal. Here we have about 2 of them. So we do that. Alright? And we multiply the last row, integrating that one. So this is going to be, when you multiply this with that, you're going to have negative x squared, then e to the power of negative x. This negative here is from this one. Here is positive. We multiply negative 2x with e to the power of negative x. We're going to have negative 2x e to the power of negative x. Remember, multiply the diagonals. Then multiply the last row and integrate it. So when we multiply the last row, that will be 2 times this. Remember the positive sign. So that will be plus the integral of 2 times e to the power of negative x dx. Like that. So you see that when you integrate a constant multiple of something, you can simply put the constant in front, right? Great. And you go ahead and integrate the other. So by integrating this, simply we just have, I multiply it by 2, we just have negative 2 e to the power of negative x. And you put this one down, negative 2x e to the power of negative x. And then we put this one over here, negative x squared e to the power of negative x. And you see all of them are with negatives. Maybe you can factor out the negative sign and put them in positive case. And even factor out the e to the power negative x and so on. But this is a nice place to stop. So you just add an arbitrary constant to that. So that is great for the second question. Let's go ahead and look at this in terms of the trigonometric expression. Alright, great. Now we now have the third case here. We have x to the power 3 sine 2x dx. So here the power is now being increased to 3. Well, you can still do this. In fact, this method makes this to be very short for us. Here we are expected to apply the integration by part 3 times, right? Because that is after 3 times, after differentiating 3 times, you're going to end up with a constant term over there. But this DI method would simplify for us because we just need to put down the D and the I and create a table from there, remembering to alternate this sign, plus, minus, and so on. Great. But we don't have to do it too much because we know we're actually going to end somewhere. Well, here we put down the one we have to differentiate, which is this one, and then we integrate sine 2x. Well, you know that the integral of sine x is negative cosine x. So sine 2x, you just have to bring the constant here to the denominator, that is negative cosine 2x over 2 when you integrate. So here we have negative cosine of 2x over 2 as the integral of that. Maybe let's bring this one down a little bit. Okay. Alright. Then we differentiate this. We're going to have 3x squared. We differentiate this again. We're just going to have 6x. Well, we go ahead and apply this for this one once more. okay, we're going to have the integral of the whole of this, all right? That will just give us negative sine of 2x over 4. Again, check that out. The integral of cosine 2x is sine 2x over 2. So the integral of negative cosine 2x is going to be negative sine 2x over 2. Since the 2 was here already, we have that over 4. So you just take that out, right? Okay, great. We differentiate this again. We're going to have just 6. We go ahead and integrate this again. We're going to have cosine of 2x over 8 as a result. That is, you integrate sine 2x, you have negative cosine 2x over 2. You notice that this was negative already, so negative sine 2x over 4 will now give us positive cosine 2x over 4 times 2, which is just the 8. So I believe you just do the integrations, then you put them back into the box. And the next thing you do here is to go ahead and multiply the diagonals, multiply this with this, multiply this with this, and then multiply the last row and integrate it, right? So maybe we need a lot of space for this. Okay, but maybe you just check that out, multiply this and this, multiply this with this, like we've done over here, right? And you are going to be putting those ones outside. It's only the last row, you multiply it, right? That will be 2 over 3. Okay, is it 2 over 3? 4, 2, 2. That will be 3 over 4. Then you integrate this. All right. So, how about this last one, this number 4? Functions like this, if you want to integrate functions like this, you see that they will never end if you want to use the integration by part. In that, when you differentiate e to power x, it's still the same thing, e to power x. When you differentiate or integrate cosine x, you have sine, irrespective of the negative. If you differentiate, you have negative sine, integrate again, differentiate again, you have negative cosine, sine, cosine, sine, cosine, alternating. It does not have an end. Unlike the polynomial that will decrease till it gets to a constant term, none of this gets to a constant term when being differentiated. So are you going to apply the integration by part infinitely many times? Okay, so this number 4 is actually quite fun, all right? And I'm going to do this in my next video. So thanks for watching, and let's go ahead and solve this in the next video. Please subscribe to my channel.